Hello friends, I welcome you in lecture number 3 on singularities and zeros. In previous lecture, we have discussed classification of isolated singularities. So in this lecture, we are going to discuss how to classify the isolated singularities of a given complex function. Before that, we just discuss different types of isolated singularities. We know that if z0 is an isolated singularity of a complex function f of z, then there exists a deleted neighborhood of z0 in which f of z is analytic, and if f of z is analytic in the deleted neighborhood, then f of z has Lorentz series representation sigma a n z minus z0 raised to n is from 0 to infinity, plus sigma n equal to 1 to infinity bn over z minus z0 to the power n, which is valid in this annular domain. So type of isolated singularity depends on the principal part of this function f of z. So if this principal part has only a finite number of terms, suppose principal part has m number of terms, say b1 over z minus z0, b2 over z minus z0 square, and so on, bm over z minus z0 to the power m. So if the principal part contains only a finite number of terms where this bm is non-zero, then z0 is called pole of order m. So order of pole depends on the coefficient bm, the coefficient which is in the numerator of z minus z0 raised to m. So if principal part contains only a finite number of terms, then z0 is known as pole of order m of a given function. Another type is removable singularity. So if this principal part contains no terms, there is no term in the principal part, that means all the bn are 0, bn equal to 0 for every natural number n, then principal part has no term, and in that case z0 is known as removable isolated singularity. And third possibility is if the principal part contains infinite number of terms, then in that case z0 is known as isolated essential singularity. So with this in mind, we are trying to classify the isolated singularities of these functions. So we discuss one by one all the functions. First we consider this function sin hyperbolic z over z raised to 4. So let f of z equal to sin hyperbolic z over z raised to 4. So we know that sin hyperbolic z is analytic everywhere. This z raised to 4 is also analytic everywhere. So this function fails to be analytic at those points at which denominator is 0, that is z raised to 4 equal to 0, and z raised to 4 is 0 if and only if z equal to 0. So this function is not analytic at only one point, z equal to 0. So if we consider any deleted neighborhood of z equal to 0, then it is going to be analytic in any neighborhood of z equal to 0, which is deleted neighborhood. So there is no restriction on the upper bound. Here we can write infinity. If we consider any deleted neighborhood of z equal to 0, then this function is analytic in that deleted neighborhood. So we can represent this function in terms of Lorentz series about z equal to 0. So here first we write that clearly f of z is analytic in 0 less than absolute value of z less than infinity. That means z equal to 0 is an isolated singularity of this function f of z. So now we have to decide that what is the type of this isolated singularity. For that we write down the Lorentz series representation of this function. So we know the Maclaurin series of this sine hyperbolic z. If you are not familiar with Maclaurin series, you can watch my lectures on Taylor and Maclaurin series of complex functions. So we have discussed what is this Maclaurin series of sine hyperbolic z. It contains only odd powers of z. So z plus z cube by 3 factorial plus z raised to 5 by 5 factorial plus z raised to 7 by 7 factorial and so on. And we know that sine hyperbolic z is entire function, so this is valid for every z. Now here our function is sine hyperbolic z divided by z raised to 4. So therefore we divide both sides by z raised to 4. So here z divided by z raised to 4, that is 1 over z cube plus z cube divided by z raised to 4, that means here we will have 1z, here z raised to 4 will cancel out, z raised to 5 by z raised to 4, that is z divided by 5 factorial, z raised to 7 divided by z raised to 4, that is z cube divided by 7 factorial and so on. Now this is valid in the deleted neighborhood of z equal to 0, 0 less than absolute value of z less than infinite. So this is the Lorentz series representation of this function sine hyperbolic z over z raised to 4. So now we concentrate on the principal part of this Lorentz series. Principal part is that part which involves negative powers of z. So we can see the principal part is can be written as, so therefore the principal part of sine hyperbolic z over z raised to 4 is, so we have 1 over 3 factorial into z plus 0 divided by z square. There is no 1 by z square term, so we can write 0 divided by z square and 1 divided by z cube. So this is the principal part of given function at z equal to 0. So here the highest power of z is z cube in the denominator, and therefore we can say that z equal to 0 is a pole of order 3 for this function. So therefore z equal to 0 is a pole of order 3. So we just recall that if we have this principal part b1 over z minus z0 plus b2 over z minus z0 square and so on, bm over z minus z0 raised to m, then if bm is non-zero, then z0 is called pole of order m. So here b3 is non-zero. In this case, if we compare with that, we can see b1 is nothing but 1 by 3 factorial, b2 is 0 and b3 is 1, which is non-zero. So because b3 is non-zero, here z equal to 0 is a pole of order 3. Now we consider second example. Second function is z square minus 2z plus 3 divided by z minus 2. Z square minus 2z plus 3 divided by z minus 2. So this we can rewrite as, we can see we can take z common here. So we have z into z minus 2 plus 3 divided by z minus 2, and this we can rewrite as z plus 3 divided by z minus 2. So we can see here this function is rational function, division of two polynomials, and we know that rational function is analytic everywhere except those points for which denominator is 0. So here denominator is 0 for z equal to 2. So this rational function is not analytic at z equal to 2. So if we consider, and it is analytic at every other point. So if we consider any deleted neighborhood of z equal to 2, then function is analytic in that deleted neighborhood. So we can represent this function in powers of z minus 2 in this domain. Now this is already in powers of z minus 2. Here we require z minus 2. So we can rewrite z as z minus 2 plus 2, and this is already in power of z minus 2. So this we can rewrite as 2 plus z minus 2 plus 3 divided by z minus 2. So this is the Lorentz series expansion of f of z with center z equal to 2 or in powers of z minus 2. So here our Lorentz series is series having finite number of terms, and this is the only term which contain negative power of z minus 2. So therefore z equal to 2 is a pole of order 1, or that pole of order 1 is known as simple pole. So z equal to 2 is a pole of order 1 of given function. So this function also has isolated singularity at z equal to 2, and the type of this isolated singularity is also a pole. We consider next function. Next function is e to the power 1 by z. So we know that 1 by z is not analytic at z equal to 0, and exponential function is analytic everywhere. So z equal to 0 is isolated singularity of this function. So e raised to 1 by z is analytic in any deleted neighborhood of z equal to 0. So therefore z equal to 0 is isolated singularity of e to the power 1 by z. So now we represent e raised to 1 by z as a Lorentz series in this neighborhood. For that we know the Maclaurin series expansion of this function e raised to z, which is 1 plus z square by 2 factorial plus z cube by 3 factorial plus z raised to 4 by 4 factorial, and so on. And this is valid for all z, because e raised to z is analytic everywhere. Here we require e raised to 1 by z, so we replace z by 1 by z in this Maclaurin series of e raised to z. So we have 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube plus 1 by 4 factorial into z raised to 4 and so on, but this is valid in the deleted neighborhood of z equal to 0. So we can see the principal part of this function is whole series because there is no positive power of z. So the principal part of e raised to 1 by z has infinite number of terms. So therefore we can write that the principal part of e raised to 1 by z has infinite number of terms, and if the principal part has infinite number of terms, that isolated singularity is called isolated essential singularity. So therefore z equal to 0 is an isolated essential singularity of f of z. And our function is f of z equal to e raised to 1 by z. So now we move towards the next function. It is sin z over z. So we check what is singularity of this function and what is the type of singularity. So as we know, sin z is analytic everywhere, z is also analytic everywhere, and sin z by z is not analytic at those points at which z equal to 0. So this is 0 at z equal to 0. So sin z by z is analytic everywhere except z equal to 0. So clearly here also sin z by z is analytic in any deleted neighborhood of z equal to 0. So therefore we can represent sin z by z in powers of z, or we can represent sin z by z as a Laurent series in this neighborhood. So for that we use the Maclaurin series of sin z, which is sin z equal to z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial and so on. So we divide both sides by z. So therefore sin z by z is 1 minus z square by 3 factorial plus z raised to 4 by 5 factorial. One z will cancel out from each term. Here we have z raised to 6 by 7 factorial and so on. So this is the Laurent series representation of sin z by z in the deleted neighborhood of z equal to 0. Now if we observe, there is no negative power of z in this Laurent series representation. So therefore the principal part contains no terms, or there are no terms in the principal part. In the principal part of sin z by z at z equal to 0. And as we know, if principal part has no terms, then that singularity is known as removable singularity. So therefore z equal to 0 is removable singularity of sin z by z. So in this way we can decide the type of isolated singularity using Laurent series representation in the deleted neighborhood of that isolated singularity. So as we have discussed, z0 is isolated singularity of function f of z if f of z is analytic in the deleted neighborhood of z equal to z0, and if f of z is analytic in this deleted neighborhood, then f of z can be represented by Lorentz series in the deleted neighborhood, and depending on the number of terms in the principal part of this function f of z at z0, we have different types of isolated singularities. So this is one way to decide the type of isolated singularity. In the next lecture, we will be discussing some shortcut methods of deciding the type of isolated singularities. So I hope you like this lecture. Thank you.